Okay, so in this video, we will prove part B of the ratio test. And if you recall, part B states that if the limit as n tends to infinity of an plus 1 over an in absolute value is strictly less than 1, then the series converges absolutely. Hence the series converges, and the series of the terms in absolute value also converges. So let's prove this. And the idea of the proof is remarkably similar to the idea that we used in proving part A. So the limit is less than 1, so the limit is equal to k, where k is some real number that is strictly less than 1. This is our assumption. And let's look at this on the real line. One thing that is clear is that k is non-negative because we take the absolute value. So let's look at 0 here. This is 1, and k is somewhere between 0. K may be equal to 0, we don't know, but it's strictly less than 1. Let me put k here. And if we ask ourselves again, what does this mean? It means as n becomes larger and larger and larger, this term becomes closer and closer to k. So we can look at a small interval around k, away from 1, and if we take n to be large enough, these terms will be inside of this interval, because they can be made arbitrarily close to k as long as we take n large enough. So, let me call this L and U, L for lower bound, U for upper bound, and again, these terms will lie inside this interval, but as we've said, as long as n is large enough. How large we don't know. The best we can say is if n is larger than some fixed positive integer, calling it uppercase n. Let's now focus on this fact and the upper bound u. So this means that in absolute value, an plus 1 over an, being inside the interval is strictly less than u, as we have an open interval, for n larger than or equal to uppercase n. And keep in mind that u is strictly less than 1. And now, let's consider the inequality when n is uppercase n, then uppercase n plus 1, and uppercase n plus 2, and then hopefully we'll see an interesting pattern emerging. So if we have this, we'll get an plus 1 over an, of course uppercase n, is less than u. Multiply both sides by an in absolute value, which will show that an plus 1 in absolute value is strictly less than u times the absolute value of an. Well, let's now take n lowercase n to be uppercase n plus 1. Let's plug it in here, so we'll get n plus 1 plus 1 n plus 2 over an plus 1. This is again strictly less than u. Multiply across the inequality by an plus 1 in absolute value, which gives you that an plus 2 in absolute value is less than u times an plus 1 in absolute value. But now we can look back at our previous inequality. An plus 1 in absolute value is strictly less than u times an in absolute value. As u is positive, or maybe 0, we can multiply u across the inequality and see that u times an plus 1 will be less than u times u, hence u squared, times an in absolute value. Let's do one more. if n equals n plus 2, and hopefully you'll see a pattern if you don't already see it. So we'll have n plus 2 plus 1 n plus 3 over a n plus 2. This is strictly less than u. Multiply across the inequality by a n plus 2 in absolute value. Therefore, a n plus 3 in absolute value is less than u times a n plus 2 in absolute value. And now let's look at our previous inequality. In absolute value, a n plus 2 is less than u squared times a n in absolute value. As u is non-negative, we can multiply across by u, and so u times a n plus 2 in absolute value will be less than u times u squared u cubed times a n in absolute value. And we can keep going like this forever. You see, a n plus 1 is less than u to the 1 times a n in absolute value. A n plus 2 is less than u squared times a n in absolute value. U n plus 3 is less than u cubed times a n in absolute value, and so forth. And now let's consider the sum of these terms. So we'll look at the sum of a n in absolute value plus a n plus 1 plus a n plus 2 plus a n plus 3, and so forth. So the entire series beginning at a n in absolute value. Well, let's now use our inequalities. A n will leave as a n plus, we'll replace the absolute value of a n plus 1 by something bigger, which we know is u times a n in absolute value. I'll write this backwards as a n times u plus, well, a n plus 2 in absolute value, I'll replace by something larger, which is a n in absolute value times u squared plus a n plus 3 in absolute value, and I'll replace this by something larger, which is a n in absolute value times u cubed, and so on. And you see what happens. A n in absolute value times u to the 4, u to the 5, and so on. And again, I've replaced every term by a larger term, so the new sum is larger than the original sum. But what's interesting now is every term is multiplied by a n in absolute value. So we can factor this out. If we factor out a n in absolute value, we're left with something that hopefully will look familiar. We're left with 1 plus u squared plus u cubed, and so forth. This is a geometric series where r is u. We are summing consecutive powers of u to the 0 plus u to the 1 plus u to the 2 plus u to the 3, and so forth. And now let me rewrite this expression and this one concisely using sigma notation. So what do we have here? We are summing a n in absolute value when lowercase n begins from at uppercase n and goes all the way up to infinity. So this series is less than a n in absolute value, a uppercase n, times the series of u to the n when n begins at 0, u to the 0 is 1, up to infinity. But as we've said, what is interesting here is this is a geometric series. r, the term that we are summing consecutive powers of is u, so in absolute value, r is the absolute value of u, but u is non-negative, and one thing we know about u is it is strictly less than 1. So we have here a geometric series where r, in absolute value, is strictly less than 1, therefore this geometric series converges. Series S. So this geometric series converges, therefore is nothing but a real number. Uppercase n was a fixed integer, so in absolute value, a sub lowercase uppercase n is nothing but a positive fixed real number, times a real number. This is therefore just a real number, so it is finite. So we have here a series of positive terms that is less than infinity, therefore is finite as well. But wait, when you have a series of positive terms that is finite, the series converges by the comparison test. But if you think about this is the series of a n from uppercase n to infinity, of course in absolute value. So all we are doing is ignoring the first few terms of this series. So if this series converges, we can of course add in the initial few terms, so from 0 up to n, and the full series must also converge. As again, if we ignore the first few terms of a series, we are ignoring a finite sum of finite numbers. The result is just a real number. So ignoring the first few terms of a series never affects convergence. So because the series of a n in absolute value from uppercase n to infinity converges, the series of a n in absolute value from 0 to infinity must converge as well. But wait, if this series converges, then the series without the absolute value converges by the absolute convergence test. And therefore, the series of an without the absolute value and the series of an with the absolute value, both series converge. Therefore, our conclusion was correct. If we go back, our claim was that the series converges absolutely, which is indeed the case. And that's it.